Okay, now we're getting to the meat and potatoes of 323 breast cancer screening and prevention. In this case, we are at a time where the doctor has ran the electrophoresis of the different genes, the DNA markers of that BRCA2 gene for each individual in Judy's family. And you can see them right here. Diana's DNA is in this lane, Jennifer's DNA is in this lane, Laura's DNA is in this lane, and Judy's DNA is in this lane. You can also see on the left side here the DNA marker scale. Remember that the basic principle behind DNA electrophoresis is that the negatively charged DNA is going to be pulled down through the porous lattice in the agarose gel, and the larger DNA fragments are going to migrate slower because they're bigger, more massive. They can't fit through the holes as easily, and the force can't pull them on them as well. Therefore, we are separating these by size, and Diana's DNA, this one right here, should be considered bigger than Jennifer's biggest DNA right here. We can also see next to it, the marker scale can tell us exactly how big those different pieces are based on previously known fragment sizes. So this one right here is known to be 603 base pairs long, kind of like using a ruler. And so anything that lines up right here with this 603 is also going to be 603 base pairs long. This one right here must be longer than 603 because it's a bigger piece than that one. Okay? So, in this situation, we want to actually know how much bigger each piece is than the other. And there's kind of a problem here. We could just sit here and figure out the exact sizes if we wanted to and figure out exactly, okay, this is halfway between that one and that one. But the problem is that an individual DNA fragment that is twice the size of another is not going to move twice as slow as the other one, and it won't go half as far as the other one. This is not a direct relationship. So instead, we kind of have to do some calculations and do some plotting of what is called a relative mobility value, this RF value. And we're going to use this for each standard marker, and that means that we're going to have different RFs for each and every one of these DNA markers, as well as the pieces of DNA from the family members. And we'll have to kind of plot this on a graph that we'll show later in a semi-logarithmic path. That way we have some sort of way to visualize this. Because it's not going to be 1-to-1 ratio. It's not even going to be 1-to-10 ratio. It's going to be a little bit more than that. Okay? So, here's what we'll do in this activity. First, I want you to get a ruler from my cabinet over here. I've got one right here. Ta-da! We're going to use the centimeter side of the ruler. Specifically, we're going to actually measure the millimeters. So remember, the millimeters, the tiny lines between the big centimeters here. There are 10 millimeter lines inside 1 centimeter. So what we're going to do is we're going to measure from the sample well up above here, the little spot right here, and we're going to measure to each fragment in the standard lane. So if I want to measure from Diana's DNA, from the well that Diana's DNA came from, to that very first one there, I would measure 0 all the way down to, looks like it's going to be reaching about halfway between 8 and 9. That's going to be 85 millimeters. And we're going to record this information in the boxes down here. You're first going to do this with the fragments from the DNA standard, meaning these individual markers right here. So take a moment to measure out each individual piece right here and record those values in distance migrated. That's the column A right here. Okay? Now that you've done that, step 2 is going to ask us to measure the distance from the sample well up here all the way down to the end of the gel where this line meets us right here. That's going to be our reference point to be able to compare between each other. So that's almost like a ratio of the distance that it traveled versus the whole distance that it could have traveled. Now this number is going to be the same for every one of our DNA markers here because these gels didn't move. So if I put 0 right at the DNA marker here, excuse me, my number could still be down to the same every single time. Looks like my number on the screen is going to be 19.9 or so centimeters, which is 199 millimeters. It doesn't matter if you get the same numbers as me. You will get different numbers. This is not a real ruler, okay? Measure that and put that in column B right here. Okay, now that you've measured the distance to the reference point, the end of the gel, which I actually measured on the paper and I got these numbers. So if your numbers are close to these, you're doing excellent. Does not matter. As long as you get close, it's fine. Now we're going to calculate that RF value, that relative mobility value, which is going to be a ratio between the distance that it traveled across the gel versus how far it could have gone through the gel, how far the reference point was. So you just literally take A divided by B, and you get this number. So 29 divided by 110 will get you, I don't know, math on the top of my head, it's going to be like 0.3 or so. Do this math, meet me back here. So now that you've calculated your RF values, you're going to need to go ahead and go get a sheet from the crates, the Activity 3.2.3 student response sheet. It's going to look like this funky graph over here on the right side. I'm going to teach you how to use this graph because it is kind of weird looking. So what we're going to do is we're going to plot the different points that we have based on how far these particular things got in comparison to the reference points. That's the RF value that we have, and the actual size that they are. For example, if I want to plot this fragment 1 spot right here, my RF value is 0.2636. I'll just round down to 0.26. That's totally fine. Let's see. 0.2 is right here. This would be 0.3 and that would be 0.4. So my 0.26 is going to be about halfway to the 0.3. So I'm going to stick around this little block right here. I'm going to go upward until I reach the spot where it says 1,353. That is not quite halfway between 1,000 and 2,000, so it's not quite to this point right here. A little bit further south than that is going to be right here. So that's my spot for fragment number 1. Same thing for happening for 0.3181, which I can round to 0.32. That's going to be inside this block right here, going on up to 1,078. So I follow my blocks up here, 1,078. Looks like it'd be right about there if I were to plot it. Go ahead and continue to plot on your paper and meet me back here. Once you've made your graph, set that aside for now, and step 5 is going to ask you to calculate the RF values for each of the DNA fragments from each of our 4 different patients here, for Diana, for Jennifer, for Laura, for Judy. So you go back up to the lanes here, and you do the same measuring that you did before, but this time just focus on the DNA fragments that you have for each lane. Now that you've done your measuring for the different DNA samples that we have, go ahead and calculate your RF value by taking the A column divided by the B column. So now that you've calculated the RF values of each of these fragments that these patients have, that we've gathered from these patients, what we're going to do is we're going to try to actually find the size of the DNA fragment by using the RF value that we have. So if we go over here to Diana's first fragment and try to find it over here on the graph, let's see, 0.436 is going to be somewhere right around here. So that would intersect with my line right about there. So I know that this fragment is likely going to be around 700 fragment-based pairs, okay? You're going to record this in table 3, which is on the next page down low on your packet. So go ahead and see what you can do. Now that you have found all the rough estimates of the fragment length of each of the DNA samples, so I have them right here recorded, you're then going to use this table here to determine which allele is present in the various individuals. So for example, 680 is closest to that 700, so that allele is number 6. 500 is going to be number 4, so on and so forth. Okay. Now let's go and ask ourselves, what does this mean? What does the different allele mean for the individual? Well, if I have a specific allele, that means I have a version of the gene that is BRCA2. BRCA2 has many different versions, including mutated versions. Well, we know for a fact that Jennifer and Laura both have breast cancer. Let's see if they have any similarities between the different fragments that they have. Looks like they both have fragment number 3. Turns out that this means that the BRCA mutation, the one known for causing breast cancer, must be located on allele 3 because it's the only one that Jennifer and Laura both share. They both known to have a mutation. They both happen to have allele number 3. Therefore, it must be allele 3 that is mutated. Therefore, Diana looks like she has allele number 6 and allele number 4. It looks like she does not have any known mutation. But Judy, well, she also has that BRCA3 allele, or allele 3 for BRCA2 gene. So it might be the case that Judy is at high risk for breast cancer specifically in this particular mutation. And that is how you do a DNA marker analysis, just like that. Okay. Now, in the rest of the activity, you're going to do a little bit more research on prevention of breast cancer and what happens in breast cancer, including hormonal therapy for breast cancer. And your last objective is to write a letter to Judy Smith from the perspective of her doctor. You did all the work as a doctor, so you get to write the letter. And you're going to explain the findings in this genetic test, telling her all about that. And you're going to explain to Judy what preventive measures that she can do to reduce her risk of actually developing breast cancer, considering that she has the genes that kind of show that she's going to develop breast cancer, but she still doesn't have it yet. You're going to also tell her what kind of options she has. You're going to use your notes to compose your letter, especially from this part 2 scenario here. And then you're going to answer the conclusion questions for me. Okay? Sounds good? Let's get her done.